So, good afternoon, ma'am. I am the
Recap pa.
representative to do the recap of Group 1's final report, which is all about the centroids. So, for the history of centroids, the term centroid is of a recent coinage, 1814. So, it is used as a substitute for the older terms center of gravity and centre of mass. So, the term is peculiar to the English language. The French use centre de gravity. On most occasions, another use terms of similar meaning. So the center of gravity, as the name indicates, it is a notion that arose in mechanics, most likely in connection with building activities. When, where, and by whom it was invented is not known, as it is a concept that likely occurred to many people individually with minor differences. So for the what is centroids? So the centroids, it is a point in a system of masses, each of whose coordinates is a weighted mean of coordinates of the same dimension of points within the system. So the weights being determined by the density function of the system. So in the centroids, there are also some simple shapes formulas to be used, which is from the shape of square, triangle, right triangle, rectangle, circle, and semicircle. And each shapes has its two bar, which is the x bar and the y bar. So the formula used in the square, for the x bar, it is side over to 2, and for the y bar, side over to 2. For the triangle, we have the base over to 2 and the height over to 3. For the right triangle shape, for the x bar, the base over to 3, and for the y bar, the height over to 3. While for the rectangle, it is the length over to 2, and for the y bar, the weight over to 2. For the circle shape, the x bar formula is diameter over to 2, or you can use the radius. While for the y bar, diameter over to 2, or you can use also the radius. And lastly, for the semicircle, for the x bar formula, you can use the radius, while for the y bar, you can use the 4 radius over to 3 pi. In the centroids also, there is also two composite figure formula. We have the x bar and the y bar. So for the x bar, we have a x bar sub 1 plus a sub 2, x bar sub 2 plus a sub n minus 1, x bar sub n minus 1 plus a sub n, x bar n over to a sub 1 plus a sub 2 plus a sub n minus 1 and plus a sub n. For the y bar formula, we have a sub 1 y bar sub 1 plus a sub 2 y bar sub 2 plus a sub n minus 1 y bar sub n minus 1 plus a sub n y bar sub n over to a sub 1 plus a sub 2 plus a sub n minus 1 plus a sub n. So that's all for the formula to be used in solving the centroids. And lastly, we have here the importance or application. So stability is the tendency of floating object rolling from side to side to return to upright position. So by the use of this, the principle of flotation explains how ships float. So the principle of flotation states that a floating object displaces a weight of liquid equal to its own weight. So like for example, in a ship floats at a particular drop, any trimming moment acting on the ship will act about a particular point on the water plane. So at this point, the centroid of the area of the water plane, and it is called the center of the flotation. So the distance of the center of flotation is read with respect to either of the perpendiculars or the midship and is abbreviated as LCF. So that's all, ma'am, for the recap about Group 1's final report, which is all about the centroids. Thank you.
Thank you, Mr. Herman. So to start our presentation, let's have Luis Sosas for the introduction of our topic.
So once again, good morning everyone, and good morning to our teachers. So we are the group 5, and today we're going to tackle about the TPC, or the tons per centimeter. So first, let me introduce the members of the group 5. So here is we have yours truly, which is SOSAS Louis J, will be tackling about the intro and the history. And then next is we have Mr. Mates, will be tackling about the definition of terms. And also we have Mr. Bajang, John Robert, but unfortunately, he will not be joining the session or the meeting today because of the situation. So he'll be recording his own video. So he'll be discussing about the formulas. And also we have Mr. PANOY Sean Christian will be tackling or giving you some problems. We also together with Mr. German Christian will be also giving you another problem of the TPC. And also we have Mr. CATACUTAN Nico also giving you another problem also. And we have lastly, we have Mr. Lucero J. Anthony who will be tackling or tackling about the application or the importance of TPC in a real life situation. So next slide, please. So here is the objectives of or the learning outcomes of our presentation. So first is to discuss the meaning of tones per centimeter immersion or TPC or TPCI. And next is we're going to explain its origins and history. And also we're going to identify and apply the formulas to problems about the TPC. And lastly, appreciate its applications in the maritime industry and daily life. Next slide, please. So here I will be tackling at this juncture, I will be tackling the introduction. So next slide. So in this illustration, as you can see, I will explain very important and useful hydrostatic parameter of the ship's hull, which is called PPC, or it is the abbreviation for tons per centimeter. Also, you can face the abbreviation like PPCI or tons, short for tons per centimeter immersion, which is both PPC and PPCI are just the same. So in the second illustration, you can observe that when we are loading the ship's draft is increasing, while in the in the third illustration, you can clearly observe that when we are discharging the ship draft is decreasing. So it is the opposite when we are loading. So when we are making the cargo calculation, it is necessary for us to know how many tons of cargo ballast or other consumables like fuel or oil we need to load in order to make our draft increasing by 1 centimeter, which is illustrated in the last or fourth picture in the slide of our presentation. Next slide, please. So at this juncture, have you ever wondered why we use centimeter in ton per centimeter and why not ton per inch or TPI or ton per meter or TPM or etc. or another, or why not using another unit of weight measurements other than the centimeter? So here is the answer for that. So the ton per centimeter or TPC of a ship at any given draft is the mass required to increase the mean draft by 1 centimeter. So here is the answer for that. So the ton per centimeter or TPC of a ship at any given draft is the mass required to increase the mean draft by 1 centimeter. So here is the answer for that. So here is the answer for that. So sorry for that. So here is the answer for that. So the tons per centimeter or TPC of a ship at any given draft is the mass required to increase the mean draft by 1 centimeter. It implies that if the vessel is loading in salt water and the freeboard check, it may be found that more cargo can be loaded to immerse the ship another few centimeters is useful to convert this to tons. This is what we call the TPC. As we all know, the TPC varies with the draft and with the water density. Or as we all know, density of saltwater, freshwater will be explained later by the other members. And also, changes in draft cause a change in displacement, and the TPC assists in calculating the change. Next slide, please. So here is what is tons per centimeter immersion. So here is another introduction for the TPCI. So it is the number of tons required to change the draft of the vessel by 1 centimeter at a given draft. TPC for short, this is the metric equivalent to tons per inch immersion, or TPC. In layman's term, it is a type of basic method to stabilize the vessel, and also the draft of the ship in which it is immersed in water. Next slide, please. At this juncture, let's now take a look to the origins of TPC. So tons per centimeter fusion comes from Archimedes' Eureka, which created the principle of buoyancy. If you can still remember, we are all familiar with this principle, which is the principle of buoyancy, because it was already explained when we are in the first year in the course called seamanship, if I'm not mistaken. So the ancient Greek, as you can see in the picture, in the illustration, the ancient Greek mathematician Archimedes discovered this when he got into a bathtub. When he got in the bathtub, he realized that the level of water went up. So this principle, or the Archimedes Eureka moment, is called the Archimedes Principle. It states that when a body is immersed in a liquid, either it is partially or fully immersed in a fluid, it experiences an upward buoyant force which is equal to the weight of the liquid displaced by the body. And next slide, please. So here in the next slide, as you can see here, there is an illustration. It's all about the buoyancy principle, of course. So the buoyancy. So here is So let's take a look. Let's take a 5 kilogram solid object and suspend it by a spring balance. Of course, the balance will read 5 kilogram. And let this be our first case. So as you can see in the illustration, there's a first case. So in the second case, or for the second case, take a beaker of water which has a small opening at the top. So the water in a beaker is filled right up to this point where the opening is, and we keep a small container under the opening. Now, slowly lower the solid object into the water, and you'll see that the reading will be a lower number as compared to the previous case. As you can see, if you compare the reading, it is lower than the previous case. So why is that? So here is the answer for that. So it is because of the buoyant force acting on the object. You have also noticed that some water was displaced. Now, in this context, we can say that the weight of this displaced water is equal to the magnitude of the buoyant force acting on the object. And that's the Archimedes principle. Next slide, please. So at this juncture, to add more information about the history or the origin of the TPC, or the tons per centimeter. So who is King Edward and what is his contribution, DI? So next slide, please. So Edward was a king of the United Kingdom and the dominions of the British Empire, and emperor of India from January 20, 1936 until his abdication in December of the same year. So historically, tonnage was the tax on tons or cask of wine by King Edward I that held 954 liters, or equivalent to 252 gallons of wine, and weigh 1,016 kilograms, or equivalent to 2,240 pounds. This suggests that the unit of weight measurement, the long ton, or the 1,016 kilogram, or 2,240 pounds, and tonnage share the same etymology. In addition, or to add more information about that, the confusion between weight-based terms like dead weight and displacement, which these terms are also discussed in the course seamanship, stems from this common source and the eventual decision to assess just based on the ship's dead weight rather than counting the tons of wine. Also, in 1720, the builder's old measurement rule was adopted by whom? To estimate dead weight from the length of keel and maximum breadth or beam of a ship or vessel, This overly simplistic system was replaced by the Morrison system in 1854 and calculated internal volume, not weight. This system evolved into the current set of internationally accepted rules and regulations. Next slide, please. So at this juncture, I will give the floor to Mr. Mates to give you or to explain to you the definition of terms. Mr. Mates?
Thank you, Cadet Sosas. Thank you, Cadet Sosas. In this time, we're going to discuss about the definition of terms. Length. The length measured between the perpendicular taken at the extremities of the ship. Breadth. The breadth is measured at the amidships from the molded line of the frame in a ship with a metal shell and to the outer surface of the hull. As what you can see below at the illustration, this is how you measure the length and the breadth. Water plane area, or WPA. The water plane of a vessel is the surface defined as the waterline of the vessel or the footprint of the vessel to the surface of the water. The ratio of the actual area of the water plane is the product of the length and breadth of the ship. Also, as what you could see in the illustration shown below, this is the water plane area of the ship. Next slide, please. Coefficient of fineness. The ratio between the water plane area, WPA, to the area of the rectangle having the same length and breadth of the ship waterline. As what you can see at the other page of the slide, this is how you measure the coefficient of fineness. Block coefficient. The ratio of the underwater volume of the displacement of a vessel to the volume of a rectangular block having the same overall dimensions. And also for the block coefficient, this is how you calculate and measure the block coefficient. Next reporter would be Cadet BADIANG.
So, formula of TPC. Since mass equals density times volume, then mass of additional slice of water equals volume of the additional slice of water times density. If the WPE or water plane area is assumed to not significantly change between the two water lines, then volume of the slice equals WPE meter square times 1 centimeter. Then volume of the slice equals WPE meter squared times 0.01 meter. Therefore, added displacement or T equals WPE meter square times 1 over 100 meter times density T over meter squared. Thus, the formula in finding the TPC of a ship is TPC water plane area or WPE times density of the water over 100. Then the another formula of TPC is TPC equals L or length times B or breadth times CB times density over 100.
So problem solving. Problem number 1. Vessel to go with 128 meters long has maximum beam of 20 meters at the waterline and a coefficient of fineness of 0.85. Entering Cebu Harbor, the chief officer wants to calculate the TPC of his draft so that their vessel can pass the harbor safely. So the given block coefficient 0.85, ship's length is 128 meters, breadth is 28 meters. So the solution for that problem is TPC equals length times breadth times block coefficient times water density divided by 100. So distribute the values 128 meters times 20 meters times 0.5, 0.85 I mean, times 1.025 or the value of seawater divided by 100. So if we calculate that one, it will result to 22.3 tons and that is our value for TPC. Problem number 2. TPC or water plane area divided by 100 times density. So MV PANOY vessel is sailing through the coastal area of Villaba Harbor. The vessel is floating salt water 2 kilometers away from the port, then floating in fresh water at the port. The master ordered the deck cadet to calculate the TPC for their ship with the water plane area of 1,420.69 meters squared in both salt water and fresh water. So here we have two problems to solve. First one is salt water and the second one is for the fresh water. So for salt water, the value of salt water is 1.025. So the formula is TPC equals water plane area divided by 100 times density. So 1,420.69 divided by 100 times 1.025. If we calculate that one, we'll get the value of 14.56 tons for the TPC in salt water. So in the next one for fresh water, the value of fresh water is 1.00. So the formula TPC equals water plane area divided by 100 times density. So distribute 1,420.69 divided by 100 times density, which is the 1.00. So if I calculate that one, we will get the value of 14.21 tons for the TPC in fresh water. So the next reporter will be Cadet Herman.
So thank you, Cadet Panoy. So another problem number 3. So at a given draft, Kukalyong vessel bound to Palumpon Port has a length of 120 meters and a beam of 15 meters. And also a coefficient of fineness of the water plane of 0.770. So the pilot requested to provide the TPC of the vessel in seawater. So for the solution, we have the formula of TPC is equals to length times B times CW times seawater density over to 100. So simply distribute each values, which is 120 meters times 15 meters times 0.770 times 1.025, which is the value of the salt water over to 100. So you can get the answers of 14.20 tons. Next slide, please. So another problem. Medallion vessel with a rectangular shape has a length of 100 meters, 20 meters in breadth, is floating in fresh water at an even keel drop of 8.0 meters. A forward hold of 12.0 meters long was the bilge. The officer of the watch is required to calculate the TPC to report it to the chief officer. So for the solution, we have a formula of TPC is equals to 1.00 times area over to 100. So simply substitute or distribute each value. 1.00 is the value of the fresh water times 100 meter minus 12.0 meter and times 20 meter divide to 100. So if you calculate that, but first subtract the 100 meter minus 12.0 meter so that you can easily calculate when you get the answer of that, which is 1.00 times 88 meter times 20 meter divide to 100, then you can get the answer of 17.6 tons. So the next reporting would be Cadet Katakutan.
Good day everyone, I am KARL Katacutan and I'm here to discuss the problem number 5. The Coast Guard of Palawan Shore saw a fishing vessel operating near the area. The Coast Guard wanted to know the TPC of the vessel. What is the TPC of the box-shaped fishing vessel operating in the area of Palawan if it has 55 meters length, 10 meters breadth, and a beam of 8 meters? So we have here the solution. TPC is equals to 1.025 0.25 times area of water plane divide 100. TPC is equals to 1.25 times 55 meters is equals to 563.75 divide 100 is equals to 5.6375 or 5.64 tons.
So at this juncture, we will have Cadet Lucero to discuss the importance and application of our topic.
Tons per centimeter immersion is important for us seafarers to learn because it helps to calculate number of tons required to change the draft of the vessel by 1 centimeter at a given draft, which is essential to stabilize a vessel. Because through knowing the draft of the vessel, we can determine the vessel if it's not stabilized or stabilized. So if it is not, we can change it, its equally. And also it can help avoid unnecessary damage to the ship and environment because we can calculate the draft of the vessel from fresh and salt water. It is because we know the salt water more denser than the fresh water. So this means that while in the fresh water, the vessel will become lighter. So by calculating the draft, we can avoid unnecessary damages to the safety of the cargo's passengers and even the crew members itself, because we can avoid aground or capsizing of the vessel. Lastly, it can strong winds and waves because the vessel is stabilized, can avoid any capsize through yaw and roll on the ocean. And
So thank you, Cadet Lucero. So here are the references of our topic. And that sums up our discussion or video presentation of our group, which is Group 5.